Hi everyone, we're going to continue our discussion of Chapter 17, talking about trees and tree data structures. Last class we looked at the basic idea of one way in which you could implement a tree. And in that class what we looked at is we looked at the way a linked list can be extended so that rather than just having a next element, it can have children. So sort of multiple nexts. And those multiple nexts create a branching structure, and that branching structure creates something that looks like a tree. We talked about the way in which we talk about this data structure using vocabulary from family trees and from botanical trees as well. A very special case of the tree data structure is a binary tree. And the binary tree is an example of a tree that just has two children. And because we know it's only going to have two children, we give it a particular name. We say one child is the left child and one child is the right child. And by building out these children, we can represent data in a particular branching way that lends itself to divide and conquer algorithms. Today, I want to add an additional constraint to that binary tree and talk about binary search trees. Now, a binary tree is characterized by a tree where every node in the tree simply has two children. It has the opportunity to have two children. It may actually have 0, 1, or 2, depending on whether it's a leaf, it has one child, or whether it's a full tree and has left and right children. Now, a binary search tree is a binary tree that has the additional property that there's a relationship in the data. And the relationship in the data is such that for any given node, its children have the entire tree that represents its children is ordered or is separated. It's not ordered, it's just separated into two groups. So that everything on the left branch of the tree, all of the data that's in the left branch of the tree, is going to be less than the data that's at the current root node. So in this picture here, we represent that as a node D. And that node D, that's a node which has a data value whose value we represent as the variable D. Everything to the left, all the children down the left branch are going to have data values that are less than D, and everything to the right branch are going to have data values that are larger than D. Within the tree, there's no relationship between siblings, it's just a relationship between a parent and the left and right child. This is a powerful property for increasing the efficiency of various operations that we might do on the tree. Here's an example of a particular binary search tree filled out with names. You can see that at the root node, the data string Juliet is present. That's what we're storing in that node. And then additionally, there's a left and right child. The left child points to Eve and the right child points to Romeo. And as you look at this, you can see that in the sense of alphabeticalness, Eve is less than or before Juliet, and Romeo is greater than or after Juliet. So left things come alphabetically before and right things come alphabetically after. Now, if it was some other kind of data, for example, numbers, the numbers to the left would be less than the root node, and the numbers to the right would be greater than the root node. If it was some other kind of data, for example, a custom class, the elements to the left would have the result of the compare to function would be less than 0. And the element to the right, the result of the compare to function would be greater than 0. So as we continue down the tree, you can see that Eve has two children as well. And Eve's children are Adam on the left and Harry on the right. So two things to notice about this particular subtree. First of all, you know that Eve is less than Juliet. Well, we can see that Adam is less than Eve and Harry is greater than Eve alphabetically. A comes before E and H comes after E. So that subtree rooted in Eve maintains the binary search tree property. But if you also notice, all of the children of Eve are also less than Juliet. And so this property of the subtree to the left being less than the root node has to hold all the way back up to the root, so that when you're at the root node Juliet, you know that all of the elements to the left are going to be less than J, or Juliet, and everything to the right is greater than J. So if we go down the right branch and we see Romeo, Romeo has the ability to have two children. In fact, the left child is null, but the right child points to a data node that has the data type. Again, the binary search tree property is preserved. Tom is alphabetically greater than Romeo, but Tom is also alphabetically greater than Juliet. There's nothing in our tree that comes between J and R, and so there's no left child of Romeo. And that's an interesting thing that I bring up, because if you look over on the left side, Harry is between Eve and Juliet, because it's to the left branch of Juliet, but to the right branch of Eve. And so this tree represents a total ordering over all of our data if you know how to get through the tree correctly. Here's a binary tree that is not a binary search tree. It's a binary tree because all the elements in the tree have either a left child or a right child, 0, 1, or 2, and no more. But if you look at the binary search tree property and you look at the node, you look at the subtree that's rooted at Adam, Adam has a left node, Eve, and Eve is not alphabetically less than Adam, it's alphabetically greater than Adam, and so shouldn't be down the left branch. Likewise, on the right branch from Juliet, Tom is alphabetically after Romeo. And so Romeo shouldn't be on the right branch from Tom, it should be on the left branch from Tom if we're going to keep it in this structure. And so this is to draw out the fact that you can have a binary tree that isn't a binary search tree, even if it's holding the same kind of data within it. We can look at an implementation of this, a simple implementation, and you can see that it's not much different than the binary tree itself. We have an overall, holding class called the binary search tree, and that holding class has a root node that is the entry point to our tree. There are some methods in there, a constructor, binary search tree, that'll construct a blank tree, and then we have a method add, which is going to add some data to our tree, and you can see that we're going to add something which is of type comparable, or that's an interface, so anything that implements comparable. What does a class that implements comparable have to have within it? It has to have the method compare to. And so what this says is we can add anything to our search tree, but it has to be something that's comparable to itself. All right, so we also have this internal class node, and you can see that we have the same things that a binary search tree has. We have data left and right, but we've constrained data. In our binary tree, data was of type object, meaning it could be any class that exists because all classes descend from object. In the binary search tree, we restrict the data to being a subclass that implements the comparable interface. Left and right are also instances of node, and then we also have a method within our node class called addNode, which is going to be a recursive helper function that enables us to add new data to our tree when the binary search tree method add is called. So the algorithm for inserting something into the tree has to maintain this binary search tree property. And so we have to do it in a very particular way. If we have an existing tree and we would like to add data to it, what we're going to do is we're going to start at the root and we're going to say, if our root node has data in it, if it doesn't have data in it, it's null, and that's fine. We can just add the data to the root node. But if it does have data in it, we have to look at that data value. And if the data value that's in the root node is larger than the value that we want to insert, we're going to recursively try and add the data that we want to add to our tree down the left branch. If the node that we're currently looking at is less than the value that we want to insert, we're going to recursively go down the right side and try and add it to the right branch. And if the data node is the same as what we currently want to insert, well, we have to decide exactly what we're doing here. But what we're going to assume is that we only want one copy of every piece of data in our tree. And so in that way, we're kind of setting up to use this binary search tree as a way of representing a set. It doesn't have to be that way, but we're just going to design it that way. If at any point we encounter a null node in this recursive process, we're going to insert the data into our tree. And so in that way, this recursive algorithm has the properties that we care about. It has a base case, and that base case is when we're looking at a node that has a null value, and it has a recursive case in which the problem gets smaller, which is we're moving down the different branches of the tree, meaning the tree that remains gets smaller and smaller. And we know it's going to end because at some point we're going to get to a leaf that has a null value in it. So here's what it looks like as a user of a binary search tree. First, we create a binary search tree, And when we add Juliet, the recursive function just starts and with a null node at the root, and so we just add Juliet. Then when we add Tom, we have to recursively walk down, and we say, Juliet, oh, that is less than Tom, so we need to go down the right branch. Nothing's there, so we add Tom to the right side. Now when we want to add Diana, we start again at the root, and we start at Juliet and say, oh, Diana is less than Juliet, so we're going to go down the left side. Nothing's there, so we add Diana. Now when we want to add Harry, we start at the root node and say H comes before J, so we're going to go down the left branch. Now we do the same comparison at the Diana branch, and we say H comes after Diana, so we're going to go down the right branch. And so in this way, we end up getting a tree that has 4 nodes that maintains the binary tree property as well as the binary search tree property. And you might notice that the shape of this tree is going to vary depending on the order in which we add the various elements into our binary search tree. So for example, if the first node that we had tried to add to our binary search tree was Diana, all 4 of these nodes would have ended up going down the right side of the Diana branch, the Diana itself, and then the 3 additional children node, because everything else is greater than Diana alphabetically. So a binary search tree is going to hold all the data, but the order in which you add it to the tree creates the ultimate shape of the tree. Finally, if we decide to add Romeo, we need to walk down the tree, and we say Romeo is greater than Juliet alphabetically. We get to Tom. Tom is greater than Romeo alphabetically, so we go down the left branch, and then we add Romeo to the left side. So nice recursive algorithm. What does that look like in code? Well, it kind of looks like this. What we do is we start with our binary search tree method add at the top here, and this is what the user calls when they want to add data to the tree. Diana, Harry, Tom, whatever it might be. The first thing that we're going to do is we're going to create a new node that's going to hold our data, and into that new node we're going to place the data that we want to have added, and we're going to create a left and right node, left and right child, which are both null. Now, this is a node that exists independent of our tree. We're just creating kind of a leaf that we're going to tack onto our tree somewhere. Now we ask if our current tree, represented by the instance variable root, is equal to null, then we just set root equal to this little node that we made, and we've added our data. But if our root node is not null, then we have to begin the recursive process of finding where we're going to add this new node. So now we call the method addNode on the root or node class, and we begin the recursive process. At the bottom, you can see the definition of the addNode recursive method within the node class. When we're given a new node, we say, okay, well, we have to do this process of checking whether it should be less than or greater than the current node. So we say, okay, here's the new node that we're interested in adding. The data within it is newNode.data. It's an instance of a comparable class, so we know it has the compare_to method within it. We're going to call the compare_to method, and we're going to compare it to the data that's currently represented in the node that is in the tree that we're descending. If the data that we want to add is less than it, then we're going to first check to see if the left node is null. If the left node is null, then we're good. We just say the left node gets assigned this new data that we're adding. If the left node is not null, then we just recursively call this method again, going down the left branch. On the other hand, if the comparison was greater than 0, meaning we should go down the right branch, we check to see if the right side is null, and if it is, we just tack on the leaf that we made. But if it isn't null, we recursively walk down the right side in order to find where it belongs. And you can see that there's no case if the comparison equals to 0, because the assumption here is that we only want one of every data element within our tree. Okay, so this is the basic idea of a binary search tree. Let's work with it a little bit and see if we can understand the way in which we build them and maintain them. Thanks for your attention.